Statistics and Applied Artificial Intelligence from Statistics Canada. John has been working in the area of official statistics on structured data and modeling for more than 12 years. Past domains of experience include the consumer price index and measures of spatial accessibility, as well as the exploration and integration of scanner data, web scraping, crowdsourcing, and open data. We have Sarah Burns, remote sensing analyst, Ag0 project from our agriculture division at Statistics Canada. Sarah has been working in the field remote sensing and GIS for 7 years following her bachelor and advanced degree. During her time at Statistics Canada, she has worked inclusively within the agriculture division, analyzing geographic data sets for various agricultural applications for the department, including digitization, classification, and emergency maps for agriculture operators. Sarah's focus has been leading projects with multidisciplinary teams, including data scientists, to experiment with automatic detection and classification of various agricultural components on our surveys and census. And then we have Marina Smills, Unit Head, Data Exploration and Integration Lab, Center for Spatial Business Project at Statistics Canada. Marina has been working on open data and geospatial analysis at Statistics Canada for over 6 years, and is one of the key contributors to the StatScan Linkable open data environment. Other than running the development open database for the Linkable open data environment, her work focuses on using open and alternative data inputs for experimental indicator development for a client across the federal government. So with that, I'm pleased to turn the call over to our presenters for their part. Thank you.
Thank you very much. So yes, so I'm Jean Moulek, and I'm here with my colleagues, and we're going to talk about a few different projects. There's a high focus on experimental work where we're doing automated remote sensing over satellite imagery, but then there's a strong connection with open data, provincial data, municipal data, open imagery, and how all of these 3 different projects interconnect. And then we have some key questions at the end to hopefully have a discussion with the audience on some related topics. All right. So one of the key messages that connect these 3 topics is how we can go from various disparate or singular open data sets and how they can be collected, standardized, processed into a larger micro level data set as well. And this is a thought, but we're looking forward to show this idea in the next 3 projects and then discuss with you. All right, there is a little bit of a lag on my side, so if the slides don't seem to be moving, please let me know. So here are the 3 different presentations. So I'm going to go first on using machine learning for automated remote sensing and showing a specific use case for detecting woody biomass or trees for in simple terms. And then my colleague Sarah Burns is going to discuss the open database of greenhouses, which was created in part through leveraging open imagery as well as automated remote sensing. And then finally, my colleague Marina is going to describe how this open database of greenhouses was released through the Linkable open data environment, as well as then that environment at a higher setting, which has all sorts of other data bases that are really built around this open ecosystem. All right, so the first one, it's a use case that my colleagues and I conducted in partnership with Agriculture Agri-Food Canada. And the goal of this project was to develop methodologies to, in short, detect trees in Canada, specifically woody biomass over croplands. And this relates to greenhouse gas reporting that AAFC is required to do for various UN projects and initiatives. This project was completed in 2022-2023. We just finished actually a 2nd phase of this work. And it was very much a proof of concept and an experiment. First, we didn't know if the imagery needed to do this test was available, specifically higher resolution imagery. For those with a GIS background, this will probably be familiar to you. And then lastly, for some of the modeling methods, the neural network computer vision models, We had some experience in the team on leveraging those, but never specifically for detecting trees. So very much a proof of concepts and a research project. There was a few challenges known right away. One is because this was research, there weren't necessarily funds available or the justification even to go purchase all the high resolution imagery that would be needed in order to train a model, which I'll discuss, and then do the test. And so one of the goals was to rely heavily on open data and other information and imagery that's available to the public, of which is actually being made available by provincial governments on their open websites or municipalities as well. So strategically, we chose a resolution of imagery to target of around 1 to 5 meters, so 3 meters, where we were looking at building a model around the red, green, blue bands. But I'll describe this in more detail as we go. All right. So in terms of the methodology, so for those who are familiar with machine learning, one of the first input data sets needed is training data or label data. For those of you who aren't, the idea with a lot of these models is that you're training it to mimic a particular cognitive task or particular task based on some gold standard of what's been done in the past. To say often it's repeating a manual task. In this case, it's fairly straightforward, where we have an image, a satellite image, and I'll go through a couple examples. And the goal is to essentially just digitize the pixels in that image that relate to trees or woody biomass in this case. Now, for this particular project, we did not have any of that training data, that label data to work with. So we had to create it. And this can usually take up quite a bit of investment as it's a very manual task. However, this project allowed us to test an automated way to generate our training data, where we're making use of height information and something called the NDVI, the Normalized Difference Vegetation Index. And I'll explain what that is in the coming slides. So before running our model on news-sided imagery, we first have to train it. And so for that, as I mentioned, we need some labels, we need some ground truth, we need previous examples of pixels that are associated with trees and those RGB values. And so on the slide here, and there'll be 3 slides or so, I describe how we created this ground truth in an automated way. So the task at hand, I've highlighted in blue. You can see the various circles where I've circled what is woody biomass. There's other woody biomass in this image other than the 3 circles, but the circles are just to show that there could be something that looks kind of like a forest, as well as some linear features on the edges there. So the idea is simple, is on this image, we want to have a digitization, a map, or for each of the pixels associated with the tree. So manually, fairly straightforward, but very time consuming, especially if we have to do this 1,000 times. So what we did is leverage 2 data sets, as mentioned. The first is a vegetation index map. And this essentially is an index where, in this case, if it has a high value, it signifies green, something green or vegetation. And so here, by using this vegetation map, we're able to find the pixels that are associated with vegetation. That means that we can eliminate all the pixels that are, say, water or are built structures, barns, roads. We can eliminate some of the fields, but not necessarily all of them. And so we're left with the orange pixels, which contain woody biomass or trees, but as well as probably some bushes and some other vegetation. So we're part of the way there. The next data set we use is LiDAR, so an HRDEM map, which is elevation. So with this, it gives you a topographical map of the objects on the Earth. And here we can apply a cutoff. So we can apply a 2-meter cutoff. This was suggested by our colleagues at AAFC, our subject matter colleagues, to say that generally speaking, anything over 2 meters is going to be a tree. It's not a perfect cutoff, but it was something that we used to test. So here with that cutoff, we see in yellow all the objects that are remaining that are greater than 2 meters. And the idea here is that we're left with just the pixels that are associated with trees. This is not a perfect method, but it was something that was implementable very quickly. And with that data, we then had the sufficient data. There are labels, a mapping of pixels associated with trees that we could use to train our data. Now, one thing that I'll highlight is that if we had LiDAR imagery for all of Canada, we would use this type of approach. We would find the satellite imagery that's available, overlap it with LiDAR, and do these maps of woody biomass using this simple approach. Now, the key is that LiDAR data is even more scarce than optical satellite imagery. And so we were able to find enough to create our training data, but the idea was really just to use this training data to create our model that could be applied thereafter on only optical satellite imagery. Now, in terms of data sources for testing, so this is for that satellite imagery that now we're going to apply our model to. There were all sorts covering various provinces, various levels of resolution as well. In terms of the training, the model specifically, I won't go into the details. If anybody is interested, they'll definitely reach out and we can have a discussion. But in short, it was a neural net model, a ResNet architecture to be specific, and it uses the RGB bands. So in the optical imagery, there's values for red, green, blue bands, and the model then ingests those bands for each pixels and then provides a prediction on whether or not that pixel is woody biomass or something else. And we're really after the woody biomass. All right, so now with our model trained, we applied it to other satellite imagery. And here's an example of the results that we get. So in the bottom, you see the visual representation to the naked eye of the satellite imagery. So that's fairly intuitive. We can see that there's a river in the middle. There's some trees. This looks like cropland. I'm from Winnipeg, Manitoba, and so this is very familiar. All these square shapes. And above there, you see the results of the model. So that's when that image is fed through our model, you see the predictions. And you see 4 types of predictions. The blue ones are what the model predicted to not be a tree. So it took in that pixel and it said not a tree. So that's the black. Sorry, not the blue, the black. The black are the true negatives. The blue are the true positives. So everything in blue is the pixel that the model predicted was associated with woody biomass. And then when we compared it to our ground truth, it was in fact woody biomass. You see the performance metrics in the top right. You see the accuracy, the F1 score, which is a common indicator for assessing performance of machine learning models. They're all at around the high 80s, 90s range. So the model was performing very well. So we were quite happy with this model. There are definitely limitations to this approach. One is, if you can see on the map, you see the cloud. And so when you look at the prediction map above, you see that there's a bit of a gap where the model is predicting that the pixels are not trees, the black pixels. Whereas if we were to guess based on the surrounding objects, those are probably woody biomass. So there are limitations and things to work through. One is how to address it when we're dealing with clouds. But nonetheless, as a proof of concept, we were quite happy with this. Now, the ultimate goal for our partners at Agriculture Agri-Food Canada was to estimate the change in woody biomass, specifically the area covered by woody biomass over croplands that is shrinking or expanding, so new growth forests or deforestation. And the way that this was done using our remote sensing model was fairly straightforward, is 4 pairs of imagery for a given area of interest. We're able to run that imagery in our model, calculate the predictions of the pixels associated with woody biomass, and then estimate an area, and do the same thing for that same geography, say 10 years later. And then the difference between those predictions, those size of those polygons, gives you the estimate of the change in area covered on croplands that is associated with woody biomass. So visually, it's very intuitive. In the left, you see an image in 2010. This is for PEI, where in the middle of the image, you see those dark squared features. So this is very typical for linear tree features on croplands. And that's exactly the type of feature that our colleagues were looking to detect and to monitor to see if they're increasing or decreasing. In the image in 2020 in the middle for the same area, 10 years later, you see that those shapes, those objects are now gone. And in fact, our model was able to pick that up. So the last image you see in beige, the model predictions of change in woody biomass. In this case, it's deforestation, or the disappearance of trees. And that was sort of the key outcome of this project, is that the outcome, where there is sufficient imagery available to do these tests of before and after, so to speak, or targeting about 5-10 years difference, you can then use it to automate the detection for change in area. So that was essentially the end of the proof of concept. In terms of the major takeaways, one is there were 2 or 3 things that we really weren't sure were going to work ahead of time. The first one was this automated approach to generating our labels. So this is using that height information and intersecting it with the vegetation index. That was shown to be, visually anyway, there's more tests that we need to do, but that seemed to have worked well. The next was developing a model, again, also a success, and then finally applying that model to 2 different sets of imagery for the same geography, and then performing this change detection. So it was a successful proof of concept. In the last year, we focused on improving the model. We're looking to publish a paper. We have the report written, and so we're hoping to release that paper along with the code as well as the data, the predictions, and make that available for others to test. And then finally, one of the major obstacles relates to scaling what I just described to an entire province or a sample that covers that's representative of Canada croplands. That is where there's a major bottleneck. As I mentioned initially, the availability of high resolution satellite imagery is not high. There's you can purchase it at times, but even there, it's not always clear that it's available going far enough back in time. And buying the necessary imagery just for this use case, economically speaking, it might not be justified yet. So we're looking at 3 different avenues to try to address this scaling problem. One is that this is not the only automated remote sensing over Earth observation data project that my team has been doing. We've also been discussing with other federal departments about their potential applications for this type of remote sensing. So maybe there's some partnerships that could be done there. There's new research being done on something called super resolution, which I'll describe in a couple of slides. And then lastly, which is one of the reasons why we're presenting here, is that the more that my team looked with some of our colleagues at provincial open data portals, municipal open data portals, there's lots of imagery that's already publicly available. And so presenting here is an opportunity for us to learn more about what might be available that we haven't found, but also because of the generalizability of this automated remote sensing, it's also to have a discussion to know about what other factors than trees are potentially of interest to users and municipalities. Is there something else in that imagery that municipalities would benefit from getting a data set for? So quickly, a couple other slides. One, these are examples of other applications for this type of technology for remote sensing. We've done tests with greenhouses, which Sarah will discuss. We've also done tests with detecting solar panels, construction sites, and of course, vegetation. So those are the 4 topics or so. There's a few other ones as well that we're investigating. So seems to be a lot of other applications to test. And then lastly, with respect to the super resolution research. So again, starting from the point of the input imagery being a key bottleneck, we decided to test this technology on imagery that's widely available. So for those of you who are familiar, or who are not familiar, the European Space Agency has a satellite constellation or mission called Sentinel-2, which produces 10-meter resolution imagery for all of Canada, roughly every 6 days. So you see that image in the top left. Visually speaking, you can't necessarily make out clearly what's going on there, but it probably looks like trees. The other objects are not clear. As a rule of thumb for these computer vision, these ML computer vision models, if you can see the object of interest with the naked eye, it's usually a good flag that will be able to create a model to detect it and automate the detection. But from the raw image on the top left, it's hard to see. On the bottom right, you see the image that's comes out after the super resolution algorithm is applied. And in simple terms, this algorithm essentially takes 10 images. So an image every week, so roughly 2.5 months or so, we get 10 images, and it sort of compresses it together to mimic higher resolution for that particular imagery. And you hear the result of that super resolution process rendered at 1.25 meters in the bottom right. And then when you compare that to the top right, which is an aerial image at 1.25 meters, you see the similarity. So we can very clearly see that, yes, these are trees. This looks like an urban area with roads, and it looks like houses. Just using the image on the bottom right, it might be hard to say definitively that those are urban structures, but it does appear to be a fairly detailed, at least compared to the input imagery when we compare it to the 1.25 aerial image on the top right. So we haven't done more tests with this process yet, but that's something we're hoping to do this year, is to see how well some of these remote sensing models can work on this super resolved imagery. So on that note, I'll throw it over to my colleague, Sarah, to describe the open database of greenhouses.
Thank you. Yeah, so today I'll talk to you about the open database of greenhouses. We also call it the ODG.
Excuse me, Sarah.
Oh, sorry, go ahead.
We have one question related to Jean's presentation. So is it okay if I go through that? So one person says, have you considered Sentinel-1 SAR?
I thank you, Martin, for the question. The answer is yes. However, we haven't tested it yet. So this is something that as we're reading more literature and getting more into the modeling, we're seeing that various groups are combining both the Sentinel-2 and the Sentinel-1 data to try to get even more signal. So we're quite early on those tests. In fact, I don't think we've actually fully tested anything yet. But I definitely appreciate the suggestion, and it confirms that maybe we're on the right track.
Yeah. Great.
So
okay.
Back over to you, Sarah.
Okay, thank you. Right, so the open database of greenhouses was a release that the Agriculture Division did in early 2023, and it's the first version of our open database of greenhouses, and it's part of the Linkable open data environment that Marina will talk about later. The open database of greenhouses is essentially a collection of greenhouse polygons, which were digitized mostly by myself over Earth observation imagery as an innovation project to experiment with automatic detection of greenhouses across Canada. Since the open database of greenhouses was released as an open data product, this gives the users the ability to use, edit, or even train their own machine learning models with the database. The ODG is part of the Ag Zero initiative, which is aiming to reduce response burden on farmers by leveraging alternative methods and technologies. And one of those experimental technologies is machine learning, like what Jean was talking about. And this is to capture greenhouses and some of their attributes. The current version of the database has 24 greenhouse polygons across 4 provinces, and they were digitized and improved through machine learning. Essentially, the ODG is a result of a collaborative effort of municipalities and provinces which continue to push open data access for vector and raster data, and thus providing high-resolution aerial imagery and willingness to have an open conversation with us to form partnerships and mobilize their data appropriately so it can be a benefit to Canadians. Additionally, we did buy high-resolution satellite imagery, and this was an advantage to us in that we were able to test our models on various sources and digitally provide higher coverage. The ODG provides flexibilities for users to aggregate the database in any way that suits their needs, while also narrowing down analysis with their own greenhouse themed analysis, such as spatial analysis, vegetation analysis, and emergency preparedness maps. Imagery sources were captured across the country with either free open municipal data sites through provincial partnerships, or received through free or paid satellite imagery through the federal government acquisitions on the ODMS site, which is meant for federal remote sensing and acquisitions, such as John and myself. One great example of a data sharing partnership is our collaboration with Niagara GIS in 2018. At the time, our team of remote sensing analysts and data scientists were looking to experiment with aerial data and automated greenhouse and solar panel detection. So our outreach with Niagara resulted in us receiving their data, their aerial data, for building our algorithms for greenhouse and satellite and solar panel detection, and we were able to provide them back all the identifiable greenhouses and solar panels within their 2018 aerial imagery. So in conclusion, this partnership such as this and availability of open data allows StatCan to leverage new technologies and modeling using remote sensing and machine learning, and in return providing new products to Canadians. So after further modeling for greenhouses, and we just finished a recent project on greenhouse detection and positive feedback regarding the last year's ODG release, we are hoping to produce a new version of the ODG in the future, hopefully the near future. This new database would be focused on automated detection of greenhouses with a date reference of 2021 for all the greenhouses. And this would also better align with our Census of Agriculture from 2021. At the end of the presentation today, we look forward to hearing your feedback regarding a potential second version of the database and how you could use the data and input on improvements. Thank you.
Thank you, Sarah. We have one question if we want to kind of go through that before Marina's. Oh, but I see that John already responded. So if David has more questions, we can kind of talk at the Q&A session then. So I think we're good.
Excellent. Can you hear me okay?
Yes.
Perfect. Great. So hi, my name is Marina Smales, and I'll be going a bit more into depth about the linkable open data environment today. So just trying to control the slides. I have control, but it is not letting me change slides. Thank you. So the Linkable Data Open Data Environment is a program that has been started just over 6-7 years ago at Statistics Canada. And at its core, it is a collection of open microdatabases released under the Open Government License of Canada. What we do is we collect data from hundreds of open data sources from federal, provincial, territorial, and municipal open data portals and other groups, nonprofits as well, whoever is kind of sharing this information. But basically, many different data sources depending on the specific subject matter that we're looking into. And the goal of this work is to facilitate open research on facilities across Canada by taking all this data, harmonizing it, and creating this value-added product that people can use for their own analysis. Next slide, please. Sorry, I'm unable to, let's see, there we go. Perfect. Okay, great. Back on track. So the Linkable Open Data Environment is a collection, like I mentioned, of all these different sources. We started with the Open Database of Buildings in 2018, looking at essentially, it started off as crowdsourcing initially. And while we were trying to crowdsource information about building footprints, we realized that there was this wealth of open data already being generated by municipalities and provinces and other partners as well. So from the Open Database of Buildings, we started to move into a variety of different subject matter over the past few years, into things like the Open Database of Greenhouses with our partnership with the agriculture team at Statistics Canada, as well as into things like healthcare facilities, educational facilities, infrastructure, recreation and sports facilities, and the other subject matter listed here as well. So over time, we've kind of collected more and more as we've had interest and outreach into various aspects of this data collection. So one example of a recent database that we released was the Open Database of Infrastructure. Version 1 was published online in last summer, around I think June or July of 2023. And it's a collection of open data on infrastructure, containing bridges and tunnels, potable water treatment facilities, stormwater and wastewater treatment, solid waste treatment, and pedestrian and cycling paths. So this was the first time we were looking at this type of data, trying to pull it together, create meaningful variables, and then release it openly with all of these data sources essentially harmonized together. So the Linkable Open Data Environment process follows these 6 main steps. Initially, we identify these data sources, like I mentioned, from various different open data portals and other groups. We collect this data mainly through direct downloading of data from these open portals, but we also sometimes will access APIs or web scrape data if the formatting is not available to directly download, if it's filling a gap that we're looking for. We process and standardize this data by parsing out address information, deduplicating various facilities. For example, if we have, let's say for the Open Database of Infrastructure, we have a data set of bridges in British Columbia, but we also have a local municipality that is publishing data about their bridges. We will deduplicate to make sure that that geographic overlap doesn't result in duplicate values. We will impute different variables and standardize some as well to make sure that if various data providers are providing slightly different ways of communicating the same information, that we can standardize it into kind of one cohesive method. And we also geocode. So if there's an address point, but no geocoordinates, like a latitude or longitude point for the location, we'll try to get that so that we can put it on a map. Since that's one of the first things that kind of people ask us is, where is this located? Can I locate it within a specific region? That kind of information. Then we'll analyze this data by kind of doing a lot of validation, comparison with other data sets, trying to basically see if what we're finding makes sense, if our imputation and our standardization makes sense and is useful, interpreting the data and looking into how we can feed it into some of our other programs at Statistics Canada and some of our other research processes as well. Then we publish this data openly on the Linkable Open Data Environment webpage and on the viewer for an interactive display. And then we also try to collaborate as well, doing things like this presentation, basically encouraging open data publication, engaging with stakeholders, getting feedback, trying to kind of put out there what we've done for people to get more information and access, even get a communication point, which we will have an email at the end of this that you can contact us for further information. Basically just creating that relationship and hearing what people want to see next and things like that. So I can do a quick, maybe I'll do a demo of the website and viewer at the very end of the presentation, just since I think I will have to share my screen. Let's see. Actually, I can do that right now. Can you see it on your end? There we go.
Yes, we can see
Perfect.
that.
Excellent. So this is the Linkable Open Data Environment Viewer. We have our main web page here, giving a little bit of information about why this project is important, where it came from, what the goal is. And then we have these components of the Linkable Open Data Environment as well. So we have our open databases. These are the listings here of all the ones I mentioned on the previous slides. You can go and access those and read more information about it, get information about metadata and the methodology we used. And we can also take a look at the Linkable Open Data Environment Viewer. This will take a second to load. So this is loading educational facilities in Ottawa at the moment. So we can see here that these are all loaded and show the different categories of educational facility. We can select a unique one and see that this is the Cambridge Street Community Public School. See, it's a public school information about the address and things like that. So this allows a little bit of an interactive component for that. Sarah, can I ask you to share? Thank you. Next slide, please. Perfect. So the Linkable open data environment is used in a variety of research projects and other analytical projects. One example that I have here is the Open Database of Educational Facilities. Again, we've used it in our spatial access measures, which was a data set that we published last summer, looking at access to 7 different amenities and services across Canada by 4 modes of active and public transportation. So this was looking at things like healthcare facilities, educational facilities, parks, other, I'm blanking off the top of my head about the other ones, but there's 7 of them. And the 4 modes of transportation are looking at walking, cycling, public transit on peak hours and then off-peak hours. So it really digs into at a neighborhood level, at the dissemination block level, which in city centers is quite small, looking at this access to these kind of day-to-day amenities that people use by different methods of that. So here we have access to post-secondary education at peak transit in Quebec City. So we can see that the highest access is kind of within that downtown core, and then becomes a bit less accessible as you move out from that outer core, with certain patches of high access and low access within that. So with this program, we do have some strengths and weaknesses to this. So first of all, it's one of the first of its kind in Statistics Canada. We really have never done something previous to this that worked with kind of location level microdata that was published under an open data license, that basically, because we're working with open data from the very beginning to the very end, we can publish as microdata. Most of the time at Statistics Canada, because we're collecting from surveys or other avenues where we need to protect the confidentiality and privacy of the data, we just can't publish to that level of disaggregation. But because we're using open data from the very beginning, we can kind of carry that through and provide complete kind of transparency about the sources and the final outputs and the location level information that people really need for some of this statistical analysis. Another thing that we try to do with this is harnessing available data and then providing that value added component, whether it's the kind of cross Canada focus or standardizing variables and providing something more cohesive that people can use. And we also create a lot of open tools and publish under an open data license. So we really want to keep it as free and open as possible throughout this whole process. But because we are collecting from lots of other open data providers and working within this open data ecosystem, we also are reliant on what is being published already. So there is weaknesses in coverage because it's dependent on the sources available, and each subject matter has a slightly different geographic coverage depending on who is publishing this data and how frequently and what kind of information they're including. We also have some weaknesses in terms of completeness because not all data sets have the same set of variables or level of detail. Again, that's kind of the decision of the data providers to figure out what they want to share for their, let's say, municipality. So we work with available data to harmonize and standardize where possible, but we are working with someone else's data at the end of the day. So the things that we look for in terms of useful data, we're always looking for clear metadata, which includes good variable descriptions that tell us what's happening for those variables, exactly what kind of information is covered in there. We're looking for units of measurement to make sure that we know if something has a length of a line calculated, maybe a length of a pipe. Is that in meters? Is it in kilometers? Sometimes we can guess that, but it's always better to have something written out in concrete so we're very sure. And things like release date and update date, things like that just help us understand the vintage of the data, what changes have been made over time, and that kind of information. We are also always looking for georeferenced data. So addresses, if they're available, are always very useful, but we're also looking for geocoordinates as well to be able to place them on a map, or even better, releasing it in a spatial data format, like shapefile, GeoJSON, GeoPackage, those types of things, so that spatial data is kind of inherent in the publication itself. But I understand that sometimes, depending on who you're trying to target, a combination of that is what works best. But even having that, like a latitude and longitude variable, goes a long way to making sure that this information can be kind of spatially located, since again, that's one of the things that people are constantly asking is, where is this? And how can I measure it against other things nearby or another jurisdiction? We also have, we're always looking for additional variables, such as for buildings, we're looking at building height. For other facilities, like in the infrastructure database, age of facility. We're always looking for extra amenity features, like for schools, the type of enrollment or the capacity, or if there's any special programs within that particular school or healthcare facility, and any other detailed classification information that kind of helps us provide more richness to the data, essentially, other than just the base classification and where it is. Some of the things that we're always looking for as well in terms of current gaps in data we notice is GTFS data, the General Transit Feed Specification. That is the routing for public transit. And we notice a lot of the time that this information is shared with Google to be available on the app, or using Google Maps. You can find your way somewhere using a local bus route, but it's not always published on a website or an open data portal. So providing that open access as well is very, very useful. We do try to reach out when we notice that, but that kind of adds a level of time and effort that has to happen to make that collection happen. And we're also always looking right now for more infrastructure data as well. What I mentioned previously, the waste facilities, water treatment facilities, that kind of thing. There's a real interest right now, especially with looking at housing and densification and city development in terms of what population can be supported, and these type of infrastructure considerations. So that is of huge interest right now, and we've had a lot of requests for that. I'll end it there, and I saw some things in the chat, so maybe we can see if there's any questions related to the Linkable Open Data environment that I can answer if they haven't been answered already.
Yes, thank you, Marina. We have one question for you, and if anyone has any other questions for all presenters, please put in the chat box. We have 15 minutes to kind of go through a Q&A session, and then we can everyone can mute their devices and ask their questions as well. So a question about the Linkable open data environment is that, do you have any data sets related to places of worship, churches, religious facilities?
Places of worship and facilities, I believe, I'm just double checking right now. No, I don't believe we do at the moment. If our cultural and art facilities database had that, it has been something that's been raised before of interest, but we have not more recently updated this one, so that is something that we're looking to include. So if that's of interest, please let me know, and we can put that as a kind of one of the main points for upgrading and updating the data set next time that we do a public release.
Great. So Matt, if you can please email Marina, that's her email is in the slide, so they can kind of provide this update for you. So we have a question that's, I think, related to each presentation. So is there any collaboration with NRCan's work on integrating a building layer for all of Canada into geospatial analysis, like their earthquake disaster risk assessments, NRCan's physical exposures to natural hazards in Canada? I think that was referring to that.
Yes, I can jump in on that. We have reached out and discussed with several colleagues at NRCan over the years about their data, and it's definitely something that we want to use for, I think there's been some recent updates that we're looking to use for our next version of the Open Database of Buildings. So they've been, when I first heard it about 7 years ago, hearing the plans at NRCan to get this going and then seeing the results from that, it's been really great to see how much useful data has been shared with that. So we definitely want to take advantage of that. We haven't put it into specific analysis like earthquake disaster risk assessment, but there are other groups across the federal government that are looking at how do we get this information into various natural disaster and risk due to climate change assessments. So I do know that there are some other groups that Environment and Climate Change Canada, NRCan, and Public Safety that are trying to integrate this data to do more granular modeling in this case.
Okay, thank you for that. And I see that there's been a detailed discussion and Q&A session in the chat box. It's great. So if anyone has any other questions that would like to kind of maybe follow up on the questions in the chat box, they can turn on their mic and ask their questions. So we have a question from said that, have any of you worked with NASA's Black Marble Nighttime Lights data set?
My team hasn't. I don't know if Marina or Sarah.
Yeah, I've used it within the Google Earth Engine environment. I've there's a need to look for greenhouses that are active throughout the year for our surveys, and I've kind of experimented with it for that reason, but it is very coarse and it's hard for us to minimize it to a specific greenhouse and understand its patterns of activity throughout the year. So it's not really something that we're looking to facilitate into our current models.
Okay, thank you.
Should there's I
John?
think a question. Yeah, there's a couple questions. One is for the super resolution question above I just saw. You could be right using the 10 different images, the raw images from Sentinel-2. That could lead good results. The logic behind testing the super resolution is that because the features that we're trying to detect, say in this case it's change in the area covered by tree canopy or the trees, is that it's fairly small. They're smaller than 10 by 10 meters. And so the concern with just using the 10-meter Sentinel-2 is that you're often going to miss the change in the area. You might report a pixel where, say, it was half. If you had really high resolution, you'd observe that half of it was covered by tree. But in the low resolution Sentinel-2, maybe it'll, in one period, it'll say, no, it's not, there's no woody biomass. And in the next period, it'll say there is woody biomass. But when you're trying to do the change detection over a 10-year period, the level of precision from that estimate could be too low. And so that's the underlying motivation for testing the super resolution, in that can it mimic higher resolution by essentially adding a bit more crispness around the edges, but it is very much a question mark. So your thought might be on the right path. And in fact, we were looking at testing exactly that, comparing the results for imagery at, say, 1 meter, and then super resolved 1 meter, and then just the raw Sentinel, and really to see how the results are changing. So that's sort of the motivation, but your point is also valid, where it's something that really needs to be tested. For the next question on the testing, oh, go ahead.
Excuse me. So David, I think, raised his hand to ask to kind of follow up on this question. So maybe if David wants to unmute his device.
It was just a thumbs up. Thank you for the answer.
Okay. Sorry, go ahead.
Yes, there was another question about remote sensing for woody biomass or trees in urban areas. So the answer is yes and no. So Explicitly, we didn't target that. However, in some of the imagery that we had, it did cover urban areas, and we did notice that it was picking up urban vegetation fairly well as also. So it is something that could be tested. Now, we haven't specifically looked at that, but just by the fact that some of the imagery we had croplands as well as some portions of more urban areas, we were seeing that you could pick up a large portion of the trees in urban settings. So it's something that could be possible.
Great. Thank you. Okay, so is there any questions for presenters?
Well, people come up with more questions. I'll highlight just two other things. One is we're presenting you here work that's looking at taking microdata, looking at microdata from the start. And in this case, that microdata can be lists of information, it can be building layers that have been already digitized, or it could also be open imagery that we then digitize to create an open layer of some micro concept, in this case, greenhouses. We have some of our colleagues at Statistics Canada that are working in a parallel way, but starting at trying to disaggregate published data to a lower level. And actually, our colleague Danielle Saint-Pierre presented to to this forum a few months past. So there's more information there on the slide as well, if you're interested in seeing that project. And as I mentioned as well, actually we've been discussing the whole way, so that's great, is that one of our goals in presenting was to understand more about your uses of the LODE, which you mentioned, whether you might have microdata or imagery that you're looking to make available that might not have entered the ecosystem yet for the Linkable Open Data environment or for the woody biomass detection, as well as if you have other ideas of objects that you'd like to see detected on, say, satellite imagery, or maybe through the release of another open database. So if definitely, we still have 7 minutes for more questions, but these are kind of some of the key things we are also interested, which is great because we've already been discussing for a little while now.
That's awesome. And if anyone wants to put their kind of questions or related to this kind of questions for discussion in the chat box, or they want to unmute their devices and talk about that, we have 6 minutes left for the kind of discussion here. Okay, so while waiting for people adding your questions or anything in the chat box, so I would like to say that our we might have a webinar in June, so we will please keep an eye on our webinar page. I'm just sharing the webinar page here, so we will post it on our webinar page, and then around 3 weeks before each webinar, we will send a notification through your email and also on the SetNet Twitter page. And also we will have more webinars coming in fall that we will post it on our webinar page as well. So stay tuned for more webinars coming. Okay, that's great. If anyone has any other questions or things to mention, please bring it here. And if not, so that was a great presentation. Thank you so much, John, Sarah, and Marina, for this informative webinar. I personally learned a lot. My background is GIS, so that was kind of very interesting for me. We kind of, Marina posted our presenters' email, so you can reach out for kind of if you want to get more updates or anything. But other than that, thank you, Statistics Canada team, for the presentation, and thank you everyone for joining us today. I hope you have a great rest of your day. And we will publish the recording and the slides on the website in the coming days. Thank you, everyone.
Thank you very much.